Welcome back to the AI Research Roundup. I am your host, Alex. Today, we're looking at a new paper called Which Agent Causes Task Failures and When? On automated failure attribution of LLM multi-agent systems. So, imagine you have a team of AI agents working together on a task, and they fail. Figuring out exactly which agent messed up, and at what specific step, is a huge headache. This paper calls that process failure attribution. The researchers propose a way to automate this. They created a big dataset of system failures, called Who&When, to train and test their methods. But the results show just how hard this is. Even the best methods struggled to pinpoint the exact error, highlighting a big challenge for making these complex AI systems reliable. And for those who want to dig into the code, the authors have released a GitHub repository. It contains all their automated failure attribution methods, plus the Who&When benchmark dataset. This dataset is built from annotated failure logs, which are essentially detailed records of system errors, complete with notes from human reviewers, explaining exactly what went wrong and when. Okay, so this first figure really lays out the whole concept. At the top, you have an LLM multi-agent system trying to do various tasks, like coding or math. When it fails, it produces these detailed failure logs I mentioned. From there, the diagram shows two paths. The old way, manual attribution, is shown in red. It's costly and needs human experts to find the failure responsible agent. The new approach, in green, is automated attribution. Its goal is to be much more efficient, using other LLMs to find not just the agent, but also the specific decisive error step. So to actually do this automatically, the researchers developed and tested 3 different methods, mostly using GPT-4o. First is the all-at-once method. This is pretty straightforward. You just give the entire failure log to the LLM and ask it to find the error. Second is the step-by-step approach, where the model analyzes the conversation one turn at a time, stopping as soon as it thinks it's found the mistake. And third, they tried a binary search method, which repeatedly cuts the log in half to zero in on the error's location. Alright, so these next charts show how those 3 methods actually performed across a range of different models, like various versions of GPT, Llama, and Who&When. The performance is measured in 2 ways. On the left, we have agent-level accuracy, which is, simply, how often did the method pick the right agent? And, on the right, step-level accuracy, which is much tougher, measuring if it found the exact decisive error step. And what's fascinating is this clear trade-off. The all-at-once method is consistently best for agent accuracy, but worst for step accuracy. The step-by-step method is the exact opposite. Building on that trade-off we just saw, this next pair of charts digs into another crucial factor, how the length of the failure log affects accuracy. These particular results are for the handcrafted systems. On the x-axis, you have 5 length levels, going from shorter logs to much longer ones. And the trend is pretty stark. For both agent-level and step-level accuracy, performance for all the methods drops as the logs get longer. In fact, for step-level accuracy on the right, the performance basically plummets to near zero for the longest conversations. So even though pinpointing the exact error step is really tough, this next set of charts gives a more optimistic view from a statistical standpoint. The top left chart shows the ground truth, which is just another way of saying the correct human-verified answer. You can see that Agent 3, the web surfer, is the real culprit in over 50% of failures. And what's encouraging is that while the methods might fail on specific cases, they all correctly identify this larger trend. All 3 methods, all at once, step-by-step, and binary search, correctly finger Agent 3 as the primary troublemaker. So we know the methods can spot the main troublemaker agent overall, but the researchers wondered if they could improve the accuracy on a case-by-case basis. They ran what's called an ablation study, which is where you test a system with and without a specific feature to see how important it is. Here, that feature was an explicit reasoning prompt, essentially telling the model to think step-by-step before answering, and the results are really clear. The red bars, showing performance with reasoning, are consistently higher than the blue bars without it. This simple instruction boosted performance across all conditions. And to really make all of this more concrete, this next figure shows us an actual example from the Who&When dataset that the researchers built. The user's query at the top is the same for both examples, asking for the lowest house price in a specific neighborhood. On the left, in an algorithm-generated system, the data analysis expert agent fails because it can't find a file, and instead of trying another way, it just decides to create a fake simulated dataset. That's the decisive error. On the right, in a handcrafted system, the assistant agent goes off track by trying to write an email instead of letting the other agents solve the problem. These examples really show what an annotated failure looks like in practice. These examples really bring the whole problem to life. As these multi-agent systems get more complex, figuring out what went wrong and why is a massive challenge. This paper takes a really important first step by creating methods to automatically find the source of the problem, identifying which agent failed and when. This kind of automated failure analysis is absolutely essential if we're going to build more reliable and trustworthy systems in the future. Well, that's all the time we have for this week's AI Research Roundup. Thanks for tuning in, and I'll see you next time. I'm your host, Alex.